You might know trig functions as things you apply to right triangles. You might use them to figure out missing side lengths, or you might use them to figure out missing angles. Usually, when using a triangle to apply trig functions, you divide one side by another. Which sides in which order depends on the function. The three main trig functions are sine, cosine, and tangent. Let's start by going over sine and cosine as an introduction to the unit circle being used to define trig functions. At some point, you may have learned from mnemonics to memorize trig functions like SOHCAHTOA. However you've been taught, these mnemonics correspond to the following relationships. Cosine of theta equals adjacent over hypotenuse, sine of theta equals opposite over hypotenuse, and tan of theta equals opposite over adjacent. In the context of a right triangle, you might know sine and cosine of a given angle to be equal to the length of the side opposite to the angle over the hypotenuse, and the length adjacent to the angle over the hypotenuse respectively. This is a good elementary definition, but it is not the most useful definition in regards to the application of these functions. A right triangle cannot be made with another right angle or obtuse angle, so you might wonder how these functions work with angles bigger than 90 degrees, since you can't form a right triangle with these. The unit circle resolves this, though. To elaborate, more useful definitions of sine and cosine arise from the unit circle. The unit circle is a circle on a coordinate plane whose center is at the origin of the plane and whose radius is 1 unit. Trig functions on the unit circle are defined by making a line segment at angle theta coming out of the origin and which ends at the boundary of the unit circle. Since this is a circle, this means that the length of this line segment will always equal 1. Remember this fact. Another important definition for the unit circle is that on a unit circle, there is a point on the unit circle pertaining to any angle theta, defined as where a ray of angle theta intersects the unit circle. Some trig functions are defined based on this point, however some others are defined by the ray of angle theta coming out of the origin. Essentially, functions are defined by, in large part, taking an angle theta and connecting it to the unit circle in some way. Let's start with defining the sine and cosine function on the unit circle as they're related. There would be two ways to define it. The first way would be to take the point on the circle pertaining to angle theta and finding the x and y coordinates of said point. The y-coordinate of the point would be the sine of angle theta, and the x-coordinate would be the cosine of angle theta. Another way to think about this is that the sine is the distance from the point on the unit circle for angle theta to the x-axis, aka the height of the line segment, and the cosine is the distance from the y-axis, aka the width of the line segment. It's also worthy to note that if the angle on the unit circle is below the x-axis, then the sine will be negative. This description means the same thing as the previous one, as coordinates encode distance. And by the way, I don't want you to think about these definitions as completely different definitions. They all relate and define each other, and they all define the same thing. Coordinates encode distance, which is why they're related. With this considered, I want you to think about the sine function as relating angle to height, and the cosine function as relating angle to width. Thinking about it this way makes it clear why this is important, rather than just demonstrating the unit circle definitions in an arbitrary way. The tangent function is quite different from these two, as it has three definitions. The most basic definition is that the tangent function simply represents the slope of any given angle theta. Just as a recap, slope is a property of any straight line, defined by taking a segment of the line, and without tilting it or doing anything extra to it, dividing the vertical distance by the horizontal distance. This is also known as the rise over run. The tangent of angle theta is the slope of angle theta. This is the most basic definition of tangent, and the definition that leads to most of its use. There are, however, two other geometric definitions that help define this function, although the second one is rather complicated and would be better off in the description. With the first one, construct a line of angle theta coming out of the unit circle, and notice how it is not a line segment or a ray, but rather a full line, and then draw a vertical line at the right side of the circle. The y-coordinate, or height, of the intersection between the line and the angle is the tangent of angle theta. To know why this is the same as the slope, we need to remember that the y-coordinate of the intersection is the same as saying the distance of the intersection from the x-axis, basically height. This works because the slope is defined by rise over run, and if you have a vertical line 1 away from the origin, and have the segment of the line also end at 1 away from the origin, then the value of the run or the horizontal line will always be 1, and the value of the rise vertical line can be any real number x, Any real number x divided by 1 always equals x, and the vertical divided by horizontal is the very definition of slope. And therefore, the number x, aka the intersection's height, is the slope. There is a third definition as mentioned, however it's far too complicated to explain here, and therefore I'll just put it in the description. One last definition for tan of x is sine of x divided by cosine of x. As a quick exercise, I encourage you to pause here and see if you can show why this is true. Just as a quick exercise, especially if you're in a classroom. What I want you to take from this is that rather than seeing the trig functions as being arbitrary definitions with triangles and ratios, they're useful ways to relate various geometric definitions to angle. The sine and cosine function relate height/width to angle, and the tangent function relates slope to angle. Having this type of intuition for trig functions helps a lot when trying to understand them. These are the three primary trigonometric functions. Based on what we learned, it might not be fully obvious how trigonometric functions are applied in engineering, physics, and the likes. Now that we've learned the definitions of the three main trigonometric functions on the unit circle, we can see how they're applied in various areas. The first three trig functions have the most applications. We'll go more in depth on the applications later, but let's get a sense for how to use these geometrically. The tangent function is particularly simple, as it represents the slope of any given angle theta. The tangent and inverse tangent function, which we'll get to at some point, lets you translate between slope and angle, which is very useful in engineering. We'll go more in depth on the applications of this later, but for now, just remember the fact that you can use the tangent to switch between slope and angle, and that this can be applied in a lot of places in engineering and physics. Sine and cosine have many geometric applications as well, although it might be less obvious how these are applied. Let's say that you want to make some sort of law, some sort of formula, that can give you the area of a triangle provided the two smaller side lengths and the angle at the bottom of one. We know from the definition of sine that the sine provides the distance from the angle's tip on the unit circle to the x-axis. On our triangle, let's think of the bottom length as the x-axis. Let's try to first figure out the height of the triangle using the sine function. As the sine function is defined, we can use it to find the distance of the tip to the x-axis, provided the length of the line segment is 1. If we want to apply this to our triangle, we'll have to figure out how to use this for line segments greater than 1, in this case 3. Thankfully, this is quite simple. Simply multiply the sine of any angle, in this case angle 40 degrees, by whatever length the line segment happens to be, in this case 3. This lets you get the distance from the tip to the x-axis for any length of line, which will come in handy when finding the height of our triangle. To generalize this to any triangle, we can start with writing this formula out by giving a variable to one of the line lengths as a, and a variable to the angle of it relative to the x-axis as a2. With this, the height of the triangle can be defined very simply as a times sine of a2. This works because the sine of the angle would provide the height from the tip to the x-axis if the line length was 1, and multiplying it by a would make it so that the sine gives the actual height, being proportional to the line length. Now we can simply use the Pythagorean theorem to work out the base, provided we have the other smaller side length along with this angle. I won't go into detail on how to apply it, but this is the easiest method to find the base length using the height that we figured out, and how to get both side lengths. And now that we have the base via the Pythagorean theorem, we can multiply the base by the height and divide by 2, giving us the area of the triangle along with a method we can use for the area of any triangle. Due to how the Pythagorean theorem is applied, it will be hard to come up with a closed formula using this method, although there are other, more efficient methods to find side length provided at certain angles and sides. They're just harder to prove, and I just think that this one demonstrates the usage of sine and cosine better. Think for a moment about what we just did there. Isn't that cool? We used the seemingly arbitrary concept, the sine function, and use it to create a method for finding out the area of a triangle with limited information. Laws like this aren't just limited to sine, you can make methods with cosine, tangent, and more. I won't go over them all, however I hope this simple method we just developed gives you a good conception of what the sine function is meant to describe, which is height in relation to angle. Now that we've seen why these functions are important, let's just move on to the reciprocal trig functions, which is just another class of trig functions. Reciprocal of x is defined as 1 over x, and this can be applied to functions too. The reciprocal of sine of x is 1 over sine of x. With the triangle definitions, you might know the reciprocal functions as being the reverse ratios of the standard trig functions. Cosine is adjacent over hypotenuse, and secant is hypotenuse over adjacent. Sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. Tangent is opposite over adjacent, cotangent is adjacent over hypotenuse. Essentially, you're taking both terms of the division equation and swapping their positions. Such an operation is the same as taking 1 divided by the whole equation. These functions, which are secant, cosecant, and cotangent, are mostly just used as shorthand for 1 over cosine of x, 1 over sine of x, and 1 over tan of x, respectively. Hence why they're called reciprocal, and while these do all have geometric definitions like the first 3, in most cases, it's far more useful to think of them as the reciprocals of the standard trig functions. The applications of these are dependent on the applications of the standard trig functions, as they're not that much more than shorthand for 1 over cosine of x, 1 over sine of x, and 1 over tan of x. Geometric definitions for these functions aren't in particular that useful. Usually they just display the applications of the functions in certain places or problems. Although these functions are quite useful when working with triangles, as they introduce new ratios which can be helpful when working with triangles. Ratios for these functions actually comprise a lot of their use cases. For example, the secant function gives the hypotenuse of a triangle with angle theta when the side adjacent to the angle theta is 1. This is because the secant ratio is hypotenuse over adjacent, and if the adjacent is 1, it'll just give you the hypotenuse since, as we know, any number divided by 1 is just the number. I'll go more in depth on this later, just remember the new trig ratios presented by these new functions are quite useful. With this newly learned information, I encourage you to pause and think about why mathematicians bothered defining these functions, rather than just using 1 divided by trig function. What might they be good for? Now let's move on to the final and broadest class of standard trig functions, the inverse trig functions, not to be confused with the aforementioned reciprocals. To understand what the inverse trig functions are, let's think for a moment about a right triangle for which we know the hypotenuse and this length. How can we find the two acute angles? Let's look back at our triangle definitions in order to solve both. Let's first look at this angle to try to figure out what it is. This straight length, 4.5, is opposite to the angle, which means that the sine of this angle x from the triangle definitions would be the opposite, 4.5, since it is opposite to the angle, divided by the hypotenuse, in this case 7. This would give us the sine of this angle x, but how do we get the angle itself using this information? This is where the inverse sine comes in. Taking the inverse sine of the resulting opposite divided by hypotenuse ratio would get you an angle that has this ratio as its sine. In simple terms, with the sine, you input an angle and output a ratio, and with inverse sine, you input a ratio and output an angle. Since it might be a bit taken, information overload, I encourage you to try doing the same thing with the other angle using the two lengths that we know. There's an inverse for every trig function, including cosine. Try to find the ratio and the inverse trig function that'll result in the angle. Just as a quick exercise to get you acquainted with these new functions, especially if you're in a classroom. Every trig function has a corresponding inverse trig function. Sine of x is arcsine of x, cosine of x is arccos of x, and tangent of x is arctangent of x, and so on for the rest. They all do the same thing relative to their corresponding trig function, which is performing as an inverse of said trig function. A good equivalent to the inverse trig functions to help understand them is the square function and the square root function. Square root is the inverse of the square function. If you take the square root of a number and then square it, you'll get the original number. Essentially, these two functions cancel out each other, and it's the same thing for inverse trig functions. Inverse trig functions have many applications. They're basically extensions of the applications of the trig functions, similarly to their reciprocals, but they're inverse. Rather than relating angle to height, the inverse sine function relates height to angle, meaning it takes in a height and outputs what angle relates to it in the way that we demonstrated using the unit circle. The inverse cosine function works in a similar way, but in regards to width rather than height. The inverse tangent is particularly useful. The tangent lets you translate angle to slope. The inverse tangent lets you translate from slope to angle, meaning if you have some value of slope, the arctangent can let you see the value of the angle relating to said slope, which is very useful in geometry. In practice, these functions perform the opposite of the operations performed by the standard trig functions, which makes them very useful extensions of the standard trig functions. As sine relates angle to height, inverse sine relates height to angle. As tangent relates angle to slope, inverse tangent relates slope to angle. Something I really want to emphasize in this video is that trig functions are very useful ways to relate different concepts to angle. Each trig function has a main function, so to speak. Sine relates angle to height, cosine relates angle to width, and tangent relates angle to slope. Knowing all of this, the triangle ratio definitions we might be more familiar with might seem ever more distant. However, it's worthy to note that defining trig functions using triangles and ratios is actually quite useful. The secant function is a good example of this. The secant function represents the hypotenuse divided by the adjacent, as you might know. This means that if the side adjacent to angle theta is 1, you can easily find the hypotenuse length of the triangle, which is simply the secant of angle theta, since secant is hypotenuse divided by adjacent, and in this case, adjacent is 1. As we know, any number, in this case the hypotenuse, divided by 1 equals the number, in this case the hypotenuse. Let's slow down and consider, how can we generalize this? If you take an angle on a right triangle, you can take its secant. Provided the side adjacent to the angle is 1, the hypotenuse length will be the secant. To generalize this, we can multiply the secant of angle theta by whatever length the adjacent side to angle theta happens to be, rather than just needing it to be 1. Hence, we found a method to the hypotenuse of any right triangle using just an angle on the side adjacent to it, all using trigonometric ratios. I encourage you to pause this video and consider, just for a moment, why does this work? Why does multiplying the secant by the adjacent to get the hypotenuse work? Just as a quick exercise, especially if you're in a classroom. This is quite a good demonstration, in my opinion, of why triangle definitions and ratios are quite useful. We've used this ratio to come up with a quick method to find the hypotenuse of any right triangle using an angle and just the side adjacent to it. Triangle definitions are definitely useful, but they should not be the definitive framework for what trig functions are. They are useful in problems that involve triangles and the angles of said triangles. Just to quickly note, you might have noticed that in trigonometry, degrees aren't always used. Radians are often used as an alternative way to measure angle instead. While we're not doing that here, and it's possible that you might already know what they are, let's just have a bit of a quick recap. In radians, 2 pi is equal to 360 degrees. Why this is used is that when using circles, 1 radian is 1 radius length, and since the circumference of a circle is defined by 2 pi times the ratio, that means that there are exactly 2 pi, or approximately 6.28 radii, that can fit on the circumference of a circle. And this applies to any circle. This means that a full circle in radians is 2 pi. This is also useful because on a unit circle, where the radius is 1, the amount of radians of a certain angle is equal to the arc length of said angle. To finish, I want to also address the graphs relating to trigonometric functions, particularly the sine wave. The sine wave is the graph of sine of x on the coordinate plane. The x-axis is the number of radians and the y value is the sine of the radian. You might have heard that the sine curve is the standard waveform. Any waveform is some sort of alliteration of the standard graph of sine of x. On the xy plane, coordinates of the sine curve are adjusted by adding various coefficients to different parts of the equation defining the sine curve. You might know about the standard waveform from physics and how there are various properties to it, such as the wavelength and such. This is the standard waveform, sine of x. Just to clarify, a periodic function, like the sine function, is defined as a function where there's some constant, aka the wavelength, where if you add this constant to any value on the graph, the value would remain the same in regards to the resulting output from the periodic function. With the standard sine wave, this constant, aka the wavelength, happens to be 2 pi, meaning that for any value of x, sine of x and sine of x plus 2 pi are the same. I ask you to inquire and to try to figure out why, especially if you're in a classroom, just as a quick exercise like I've done before. Now, I won't go into much more detail on how to manipulate sine curves, but you might be wondering, why does any of this matter? Waveforms are very ubiquitous. They appear everywhere in physics. In fact, they're one of the most useful concepts in physics. I won't go into too much detail, but waves describe everything from ripples in water to the properties of light and sound waves. They're also useful for describing physical phenomena such as oscillations. As a weight moves up and down on a spring, the movement of an oscillating weight is the same as the vertical movement of a point moving across a sine wave. Being able to describe and manipulate sine waves, which are the standard waveform, is very useful when describing these phenomena. A good example of this is wave interference. Wave interference, in simple terms, is when two waves are added together to form a new one. Constructive interference is when two waves combine to form some larger one. Destructive interference is when two opposite waves combine to form one, and in the process cancel each other out because they're opposite. This is especially useful in describing sound waves, as the aforementioned destructive interference is used in noise-canceling headphones. Whenever a sound is taken in, another sound of opposite wave structure is created and they cancel out, just forming a straight line. It is worth noting, however, that in most cases waves are not physical depictions of concepts like light and sound, but however, they are very useful in describing them. Light isn't composed of literal sine waves that go up and down, but wavelength and amplitude and such, as described by waveforms, are all very useful in describing different types of light or sound. Actual details are a lot more nuanced. Look up wave-particle duality if you want to know more. You might also wonder, why is the sine curve the standard waveform and not some other function? For starters, we must establish why a periodic function like the sine function is optimal for modeling waveforms and things like sound, light, etc. A periodic function like sine has two properties that are quite useful for modeling these things: amplitude and wavelength. Amplitude is the height of a wave from the x-axis, one of the two main properties used with waves. These two can be used in various models of the things mentioned earlier to describe various properties of them. For example, the pitch of a sound wave is affected by the amplitude. To answer the question, for one, the sine curve is the most easily defined periodic function by far, and most other periodic functions are deviations of the sine or cosine function. It also has a lot of desirable characteristics. The particular waveform happens to be useful in modeling a lot of various physics phenomena, such as oscillations and pendulum. You can see that each of these describe a movement where it accelerates, slows to a halt, and then goes to the other way and repeats. This is exactly the movement described by sine waves, and because of the amount of these physical phenomena that sine waves happen to describe, the sine curve also happens to be very helpful in calculating velocity and such in these phenomena. It's also quite worthy to note that the sine of the standard waveform is not arbitrary. It's more than just convenient. There are a ton of physics problems and equations that very naturally lead to sine waves as part of their solutions. Of course, I can't try to explain these in this video, as it would take quite a while and it would be quite far from the point. However, I just want you to know that the choice of sine waves is not just because it's convenient, because it comes across naturally in a lot of different physics equations and phenomena. And that's about it. I hope this video was a good overview and gave you good insight about trigonometry and why it's useful, past the standard definitions that you might already know. Thanks for watching. Bye bye.